Good morning, everybody. My name is Steve Patton from Telesoft Technologies. So first, I'd just like to say thank you for choosing to spend some time with me this morning. I realise you have a choice, so thank you very much. Telesoft Technologies are really, we're a hardware company. We build hardware devices that are integrated into other people's systems, and they do things that actually are harder to do in software. And I'm going to show you some of those things today, and you may agree or disagree. I hope you're going to agree with me. And I'll show you how they specifically apply to some of the tasks that we have to perform in cybersecurity. So at school, my daughter starts each day with a character called WILT, and WILT stands for What Will I Learn Today? So this is my WILT slide. So I'm going to look at some of the standard building blocks of cybersecurity systems. Some of you may be familiar with those, some of you may not. Actually, can we just have a quick straw poll? Who would describe themselves as, a user of cybersecurity systems? Maybe an IT department. Okay. Is there anybody here who represents an organisation that would build cybersecurity devices, hardware or software or systems or appliances? Anybody? Okay. All right. So a mixture. So, we're going to talk about perhaps some of the things that the gentlemen that put their hands up then, the kinds of technologies they might use when they build cybersecurity systems. Some of the problems that we face in building our cybersecurity appliances, how we can solve those by using a combination of hardware and software. And that's hopefully interesting because the trend really is, don't we do everything in software now, Steve? Well, yes, we do, as much as we can, because servers and silicon and x86 silicon is fairly cheap, and Moore's law drives processing power and hopefully helps us reduce cost. But as data rates in networks increases, it's going to get harder for those processors to keep up with the data. So maybe an alternative title for this session would have been using a combination of hardware and software to build cybersecurity systems. So hopefully that meets some of your expectation when you made the choice to come and spend some time here this morning. Okay. So let's imagine we've decided we want to build a cybersecurity device. What are the kind of things that we need to do? We're going to capture and analyze flows between different computing devices. And once we've captured those, we're going to have to filter through gigabytes, could be even terabytes of data, huge amounts of data. And in that data, we want to identify threat signatures, data patterns, to see if there's something there that we think shouldn't be, that could damage our device or our network. I want to have 100% visibility, and that, obviously that's one of the cornerstones of cybersecurity. If we miss one packet, one signature, one identity, that means a threat or some malware can get through to our end users or our device or our devices. And as always, I'm a commercial organisation. I need to build to a cost. I've got some cost targets. So money always is an object. So the end game of all of this is to detect and prevent intrusions. Okay, so what tools do we have? This isn't a complete toolkit, but it's just some of the things that system builders commonly use. We have off-the-shelf software. There are commercial organisations that will sell us DPI, Deep Packet Inspection software. I'm going to talk a little bit more about DPI in the next few slides. There is open source, freeware, so no money at all. And there's a list of IDS, open source and freeware providers there. The one that I'm particularly familiar with is Snort. There are others. And, of course, off-the-shelf servers. And I said there with some gigabit Ethernet ports. So I can buy a server from Dell, HP, IBM, some open source software. I can combine those two together, and I can build, a fairly fully featured IDS, intrusion detection system, or even an IPS, intrusion prevention system, for a reasonably low cost. And there are many proven designs built using this combination of tools. So DPI, people familiar with DPI? Some are, some nods and some shakes. Okay. So this is actually the definition from Wikipedia. It's quite a mouthful. So deep packet inspection is the act of any IP network equipment which is not an endpoint of a communication using non-header content, typically the payload, for some purpose. So what we're talking about there, we're probably all aware that in our IP networks, the networks that we're looking to protect and the networks that allow our users to transmit data to each other, data's transmitted and carried around in packets. It's chopped up into packets. And as that data transverses the network, we have routing functions, and those routing functions add layers and add their own header, and so our original data that we chopped up from our users kind of grows out in layers, and that's what it looks like in the network. Well, deep packet inspection is the act of actually looking deep, sort of inside that packet, peeling back the layers to try and get to the data that our applications and our users are sending, because we want to know if there's anything in there that will harm our network. And in IP, for those of you familiar with protocols, DPI is normally the act of looking deep inside our packets beyond TCP, UDP, Transmission Control Protocol, User Datagram Protocol layers. So those are protocols that are used in IP networks to transmit data. And DPI, as a technology, really at the end of the day, it's used for identification and filtering. So it's the picture there, magnifying glass, looking at lots of ones and zeros. We're looking deep inside the data because we want to see in the network what's going on. Okay, some other technology we might use. You might hear people talk about flow tracking. And that's, flow tracking is a fairly basic filtering operation. It's not really deep packet inspection because we're only looking at the outside of our packets, at the headers. And you may hear people in the industry talk about 5-tuple filters or NTuple filters. And I'll talk about that in a moment. And that's a name we give to a particular type of filtering and packet identification that we use to identify flows. 5-tuples common in firewalls, and the end goal of using this technology we call 5-tuple, is to determine which packets belong to a communication or a flow between two specific computers. So imagine a network. We have many, many devices. They're all talking to each other. And actually, I'm just interested in that one over there talking to that one over there. And I just want to pick out all the packets in my mixed network that those two are using. So that's what this thing called NTuple does. So NTuple, or 5-tuple, it's a collection of attributes, commonly 5. And in IP, we're talking about things like source IP address, source port, destination IP address, destination port, destination protocol. 1, 2, 3, 4, 5. So that's 5 attributes, 5 pieces of data that I'm going to look for in my IP packets as they transverse the network. Okay. And, some of you probably are very familiar with those, some not so, but I guess, you'll be aware of IP addresses, certainly, and maybe port numbers. So these are pieces of data that every packet carries, and every packet that is routed between the same two endpoints will have the same set of these. So we can use those to filter access requirements in firewalls, and we can identify suspect flows. So maybe perhaps a diagram might help our understanding. here's a stream of packets going across a network. That's what each one of these represents. There's 4 packets there. So 2 users are transmitting data to each other, and that data has been chopped up into packets. It's been encapsulated by different parts of the network that the data is flowing across. And each piece of network and protocol adds its own piece of information to the original user's data, or the payload. And so there we've got destination port, source port, destination address, source address, and protocol. So in a piece of cybersecurity equipment or cybersecurity software, an appliance, I can say, I want you to look for these 5 attributes on every packet, and if they all match a specific set that I've pre-configured, then that packet belongs to a flow of data from that computer to that computer. So I can pull out every packet. So that's hopefully a useful thing to do. Yeah? People agree? I think it is. Yeah. I think it's a useful thing to do. Good. Okay. So that's one of the tools we can use. 5-tuple, quite often though, isn't enough, because it will identify the data that's being transmitted or shared between 2 endpoints. But those 2 endpoints might, I don't know, they might be sharing Facebook data or email or HTTP web or IMAP or all sorts. Video, could be anything. There might be some, I don't know, viruses or malware in there. So I need to look past all those header fields. So that's all my routing information. I need to look past that, and I have to look inside the payload. Got to look deeper. So with some enhanced filtering capability. And the picture there is, it's peeling back the layers of an onion, and that's really what we're doing. If you imagine that the data that's sent around our networks, it's like an onion. It's got lots of layers, lots of onion skins around it, and we keep peeling back the layers because we want to get to the heart of what's inside, and that's our users' data, and that's going to have some interesting things inside it. Okay, so past our 5-tuple, we've got pattern and signature matching. I'm going to look inside our packets, and I want to look for strings, 1s and 0s, numbers at certain positions, and they could be virus signatures. It could be a prohibited word in a firewall. We might decide that we don't want our employees looking at a certain website. I don't know. Perhaps you don't want them looking at BBC iPlayer through the daytime. You'd much rather they were actually working. Probably, I would imagine. So maybe the word iPlayer. Perhaps you want to find that in one of these packets. So here's a diagram here. Actually, in this one relates to a voice over IP packet being sent down an IP trunk using a protocol called SIP, and I just picked out two pieces of the protocol, invite and the word SIP. I'm going to look for those, and I'm going to stop my users sending out any voice over IP, because I don't want them sending voice over IP over my network at work. Maybe perhaps it's a good thing, maybe it's a bad thing, but maybe my IT manager has decided for some reason he doesn't want it to happen. But we're looking past all the header stuff. And the final thing, we've got DPI. Sorry, we've got 5-tuple, we've got DPI, and then the third piece of technology we might use is some traffic analysis. And the place where we probably want to do that is if a user is encrypting their traffic. So let me just go back here. I can probably still look at the header information, so I can identify the information going between two different computers. But if they've encrypted, so they've hidden the data that's inside because they don't want me to look at it because they think that's what I'm going to do, then I've got a problem because I can't see things like invite and SIP and iPlayer because it's all jumbled up. So the other thing we can do there is just look at maybe the packet sizes, how much data is being sent and where it's going to. We can just look at typical patterns. So maybe I've looked at people that use iPlayer and I know kind of what an iPlayer data flow looks like on the network. So without actually knowing what's inside, I know what that profile looks like. And if I see one of my users exchanging information that kind of matches that profile, I could think, I think you might be doing something that I don't want you to, so I'm actually going to stop you from doing it. So those are three pieces of technology we can use: 5-tuple, DPI filtering, and traffic analysis. So collectively, we're all now engineers, or we're beginner engineers, and we can build an intrusion detection system, an IDS. Do you think? Do you think we can? I think we might be able to. So what things might we need? We're going to need some hardware. We're going to need a server. We all use servers. They're going to come with 1 gigabit ports. Might need to add a few more. I'm going to need some software applications to run on that server. And maybe I'm going to use something that's freeware, this thing called Snort. What a great name. Or I might buy some commercial DPI software and write my own application to work with that. So I'm going to end up with a device that looks like that. There's a Dell, an HP, and an IBM there, so I don't upset anybody's purchasing priority. That's good. That's great. And many people do this. Some people buy IDS systems off the shelf. Some IT managers build their own because they don't trust anybody else's, because they're a suspicious lot, IT managers. Or the ones that I know are. Don't trust anybody. Okay. So imagining that we do that, what's our challenges? Rising data rates. Everyone talks about rising data rates, and that's fantastic. It's good for network operators because they can charge more. So in the enterprise, 1 gig Ethernet is common. 10 gig is becoming more common, I guess. Yeah, everyone using 10 gig users? Yeah, some nods. No, yeah. Inside, data centers, medium to large data centers, there's 40 gig. There's 100 gig inside big data centers. Inside the likes of, Facebook, Amazon, Yahoo, those guys. They have massive, big 100 gig pipes and lots of them. Ever-growing protocol diversity. So we're getting more and more things happening across our networks every day. People are doing more and more things. Every day there's a new application, which means there's a new protocol. There's different types of data to look at. So my poor IDS system that I built a second ago from the servers and the free software is going to start to struggle. Because those two things, rising data rates and more protocols, consume CPU resource. They take up power in my servers. And that causes me a little bit of heartache because it drives up the cost. And I don't like spending money. Excuse me. I certainly don't like spending money on IDS, so I'd rather not have to spend money on IDS. Okay. So imagine one of those situations has occurred. We've upgraded the network. It's now not running at 1 gigabit, it's running at 10 gigabits. So let's build a 10 gigabit IDS. And I'm going to do it in the same way as my 1 gigabit IDS, but my server component, my thing from Dell or HP or IBM, is going to have to process 10 times the amount of data. So that's going to cost me more. It probably doesn't come with 10 gigabit Ethernet cards, so I'm going to have to buy some of those. There you go. So server plus a commercial off-the-shelf 10 gigabit card. Not rocket science, but it's it's costing more. Now, as data rates go up, and as the number of points that I'm monitoring increases, one of the bad things that might happen is data loss. And what causes data loss? Well, we talk about drop packets. If my detection system is trying to grab all this chopped up data as it comes into the system, and it has to look inside each packet for addresses and headers, or maybe it needs to look past those headers because it wants to find threat signatures, and I'm actually throwing more and more packets at it, at some point it's going to say, whoa, 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 can't keep up. Right, I'm going to throw those next 200 packets away because I just, I can't cope with it anymore, and then I'll start again. Well, that's, in cybersecurity, that's a bad thing, because those packets that are dropped or thrown away may be the very ones that will tell me I've got a problem coming into my network. So packet loss really isn't acceptable. And as an IT manager, that's something that would probably concern me. What else can happen? There may be a delay between detecting that we want to look at something. So I've suddenly discovered that one of my users is doing something a little strange or unusual, and that's, it's triggered me to say I need to go away and look at that flow to find out what's going on. So that's said, right, start looking, and by the time I've actually grabbed the data, they may have already shared some information. I might have missed the start, because my system's just not that fast. It's not fast enough. When I say, go, capture all the data now, I'll say, yeah, I've captured those packets there, but those first few I missed those. I wasn't fast enough. Is that okay? No, probably not. And, we may even get larger delays. So we might have our users exchanging information in a session, and maybe a few seconds in they do something that triggers my suspicion that something bad is happening, but actually they've already had seconds or even minutes of conversation that I've missed. And, my paranoia makes me think I need to know what went on before the trigger to start looking at the data. So, data loss is a concern. So we can solve some of those problems by adding more CPUs, more silicon, more memory. So more CPU, more memory, more speed. So that's the quick fix. But the problem is, of course, that it's going to cost more money. And a 40 gigabit system is typically 15 times the cost of a 2 gig system. But you're going to say, but Steve, Moore's law says that CPUs get faster and cheaper, and yes they do. But as CPUs get faster and cheaper, what happens to the amount of data that we send down our networks? Hey, that goes up too. So the very data that the CPU is trying to look at is increasing because the CPU can go quicker. So we're always trying to play this catch-up game. I think some people agree with me, at least. I saw some nods. All right. So what can we do? We can use one of those pieces of technology we saw early on. Remember NTuple and 5-tuple, looking at the address fields? Yeah, good. So we can use that filtering technology to identify the flows of information that come from different computers, and then we can split all those flows out if they're mixed together in a big data pipe, and we can send each flow off to a separate processing engine. And we'd end up with a system that looks something like this. It's quite a complicated diagram, but basically lots of data is coming in here from many, many computers. Is that in focus? Oh. Maybe that's a bit better. So lots of information coming in here to a 10 gigabit network adapter, but it might even be a 40 or 100 as data rates rise. And I'm saying I'm going to struggle to process all that on a single system. But what this one can do, it can identify the flows from individual computers, it can split it out, and then send it out over, I've said 4 times 1 gig adapters here, and I can have lots of these IDS systems, intrusion detection systems, each processing only a smaller amount of the data. So that's one way to solve the problem. But it sounds like it might be quite expensive because, you know, I've got this system here, I've got to pay for this, and I'm going to pay for lots of these. So if that's not an option to have lots of systems, the architecture we just spoke about, well, I'll just go and buy a really powerful compute platform because I know the computer manufacturers can make those, you know, really big pieces of tin, large bits of plumbing. And they might look something like that. Probably not, but that's an extreme. So maybe, you know, maybe that's really not an option. And, you know, leading edge powerful servers and compute platforms are, you know, very expensive. Or the other way is we could try and offload some of that processing and filtering that we talked about, DPI, 5-tuple, profiling, into our network interface card, into our 10 gigabit card. Because you remember we added a 10 gigabit card to the server earlier. And that looked like, so that's actually a dual 40 gigabit card there. So we have this notion of accelerated network adapters. And you'll see these in the industry. There are, you know, a collection of manufacturers that make these. And these are specialist pieces of hardware that have 10 gigabit, 40 gigabit, and 100 gigabit interfaces. But actually built inside them, they've got processing to do NTuple, DPI, and profiling. So they're going to help my software that's running on the server to do its job of looking at all the packets and hopefully ensure that I don't miss any information. It'll kind of help me sleep at night. It'll ease my paranoia. So just looking at a comparison, this is trying to represent what we would uncharitably call a dumb network interface card, the kind of thing you'd find on a server that we buy off the shelf. 10 gigabit Ethernet coming in, it's going into a capture card, I'm capturing everything, and my piece of software running on a multi-core system is, you know, it's doing some classification and filtering, it's a cyber application. It's only, you know, it's identifying certain flows and certain users, and there's possibly a lot of stuff that it's not interested in, that it's throwing away. And as this increases, you know, the work that's happening up here is getting harder and harder. And maybe it's just not possible to do that. And I have actually seen some articles that talk about cybersecurity systems running at 40 and 100 gig, talking about things like, you know, best efforts. And kind of a best effort cybersecurity system doesn't sound like a cybersecurity system at all to me. It sounds like something that doesn't really quite work. Okay, so maybe the solution, or a solution, is we'll do a bit of pre-processing, or maybe quite a lot of pre-processing, right down at the point where all these packets, all this data, comes into my cybersecurity system. So I'm going to do content matching, signature matching, DPI, layer 2. And I'm going to look at all the packets, but all the stuff that I don't want to look at any further, because I've decided those users aren't doing anything harmful, I'm going to throw that away before it actually even gets up onto my multi-core x86 server. So my host system's actually running a lot slower, a lot calmer, a lot cooler. Right. We talked about missing packets because we didn't notice that a session had started. There's some latency. And that's what this diagram is trying to illustrate. So I know it's going back to a point, but hopefully it will help us understand. Here's a stream of packetized data that's flowing through a network. And the dotted line represents a window that I'm kind of looking at. Imagine if you're looking at cars going down a motorway and you're looking at them through a pair of binoculars. Yeah, and you're only looking for red cars because you're paranoid about red cars. You think they're dangerous because red's a dangerous colour. And so you've got your binoculars, you're looking, and there's a red car over there, and there's a red car over there, but it's not in your line of sight, so you can't see it. And then red car goes down the motorway, and then, right, that's it. It's in your field of vision, and you see it. So that's what this is. This is our binoculars looking into the stream of packets. And inside, well, the blue packets belong to a flow between two particular computers. And inside this packet, there's a signature, a threat signature, that's triggered me to say, there's something wrong going on in here. I need to look at the communication between these two computers. But those two over there have already gone by. The red car's already passed by. It's headed up north. It's past my binoculars. Can't see it anymore. So I've missed some data. So that's one thing that can happen. Bit more complex still. This is a little bit of an eye chart. Sometimes the control of the session when users are exchanging data, and the actual data they're exchanging, might be separate. It's almost like having two different conversations. Saying, can we talk to each other? And you'll say, hopefully you'll say yes. But the actual information that we hand to each other, I write something down and hand it to you. So there's two different kind of methods, two different media of communication there. And that can happen in IP networks. It's more common in telecommunications, in telecoms and voice and data on mobile networks. But with the convergence of voice and data, they're pretty much the same thing these days. This is something that will increasingly become a problem for the cybersecurity community. So I've got packets down here, or information that's flowing, that's telling me about conversations or sessions starting between systems. And up here, I've got the actual content of those conversations. And because they might travel down different paths, they might be routed differently, they might end up somewhere slightly different. My start event, which triggers me to start looking at the content, might be received after some of the actual content itself has already passed by my binoculars. It's passed by the window that I can see everything. So I'm going to lose data again, which is not a good thing. So how can you stop that from happening? Well, I could store everything on my host server. I could buy lots of storage or an external storage device. But remember I said I don't like spending money. That's going to add complexity and cost. Or, remember those smart line cards we were talking about? I'm desperately trying to get you interested in and to buy. Maybe we can put some packet buffers and some memory on those cards. And again, commonly that's a technology that's actually used. To combat latencies in system, we need a buffer for 300 milliseconds. If we're worried about telecommunications type systems, we need a buffer that manages up to something like 2 to 3 seconds. Lots of delay, lots of memory. So, we're almost at the end. So here's my integrated, intelligent interface card. It's got lots of packets coming in. The yellow ones belong to a particular flow between two computers. The blue ones are a different flow between two different computers. Inside my intelligent card, I'm going to do some filtering. I'm going to chuck out all the white packets because I'm not interested in those, because I'm only interested in the data that's flowing between these maybe 3 or 4 computers that I suspect are doing something unusual. Stick those in a buffer, maybe for a couple of seconds, and then I'm going to further inspect those. And I've decided actually that the blue ones are okay, they're not doing anything nasty. But actually the yellow ones I'm not so sure about, so I'm going to send those up to my software application running on a host computer and look at those a bit more, in a bit more detail. So there are a few manufacturers of these on the market, and you'll hear people, and they're also known as hardware accelerator cards, accelerating capture cards, load balancing network interface cards, or network analysis adapters. So in summary, by sharing the filtering and processing load that our cybersecurity applications have to implement to do what they do, but by sharing that between a CPU, software, which is the trend, and an intelligent line card, we can build smaller systems, much smaller systems actually, which allows us to save on power. That's an increasing concern in industry today. Many companies talk about their green credentials. We can save on component cost. Don't have to buy a massive server, a big piece of tin. We can save on space, which may be a problem if in the data center or wherever this is being installed, the original plan didn't actually allow for this extra piece of protection equipment to exist. And also eliminate packet loss. Help me sleep at night. Eliminate my paranoia. And the picture there is really saying, by building our systems using these technologies, we can build something like my soldier ant. It's small, but it's powerful. Okay. So guess what? I know a company that does this. So if you would like to know more, please come and talk to myself, one of my colleagues. We're outside, or take a look at our website. And I'll leave you with a quote from Einstein. So, really I'm saying there, there's not always one way, there are sometimes different ways to solve problems. Okay, thank you very much for your time.